We're going to look at the difference between mass and weight. Both of these words you've probably heard before, and you might actually be using them wrong. So what I'm going to do is define each of those and then give examples for what mass is versus what weight is in terms of numbers, and then how this will all apply to forces. Mass is the amount of matter that makes up an object. So it's pretty much how many atoms are in you. It's never going to change unless the object itself has changed. So what that means, your mass will not change. If you were to go to the moon, you would still have the same amount of mass unless you lose weight. So if you go on a diet or gain weight, so you get thinner, you get heavier, that's the only way your mass would change. The symbol for mass is just a lowercase m, and the units for mass are kilograms. If anything is in grams, you're usually going to want to convert it to kilograms. There are 1,000 grams in a kilogram. But the main unit for mass, the SI unit, is a kilogram. And next we have weight. Weight is the force of gravity on an object. So it's how much the Earth, or if you're on the moon or any other planet, it's going to pull down on you. Most of our problems will be dealing with the Earth. So when we say weight, we're talking about how much Earth is pulling down on you. Since weight is the force of gravity, the symbol is Fg for force of gravity. Since weight is a force, the units are newtons, and the equation for weight, Fg is equal to your mass times little g. And we've seen little g before. When dealing with kinematics, it's the acceleration due to gravity. So Fg is weight, which is the same thing as the force of gravity. It will always point down. M is the mass, and G is the gravitational field strength. So how is that different than acceleration due to gravity? It's not. The only thing that's going to be different are the units. So we already knew that G was equal to negative 9.8 meters per second squared. When dealing with forces, and this was when it was the acceleration due to gravity, when dealing with forces, G is going to be 9.8 newtons per kilogram. A newton per kilogram is the same exact thing as a meter per second squared. The reason that this G is not negative is because when you make a force diagram, Fg always points down, again, unless you're looking at the Earth and drawing a force diagram for the Earth. But any other object on Earth, Fg will point down, so the negative that should be here, so the negative from here, will be here when you look at the force diagram as a whole. And when we get to quantitative force diagrams, you'll see how this works out to be negative. So when using the equation Fg equals mg, we're using the positive 9.8 newtons per kilogram for g. And it will work out to be negative when we start doing force diagrams with numbers. So how do the units work out? Say you have a mass of 10 kilograms and you're looking for the weight. Weight would equal 10 kilograms times 9.8 newtons per kilogram. The kilograms cancel, so weight would equal 98 newtons. So that's why we want to use newtons per kilogram as opposed to meters per second squared. It's not wrong to use meters per second squared because it's actually the same thing. When we get to Newton's second law, we'll see that inside a newton, so if you were to look at the units that make up a newton, you have a kilogram times the meter per second squared. So a newton divided by a kilogram, the kilograms cancel, leave you with meters per second squared. So the number's the same, it's representing the same thing, how much Earth is pulling down. One is considered an acceleration, one is considered a gravitational field strength, but when looking at the units, they will reduce to each other. And again, whenever we're solving problems, we're going to ignore the negative for Fg equals mg, because the negative will be taken care of when we draw the force diagram, and weight points